This talk is not exactly related to the Levinson method, but I guess yes, it has some relations with that. Okay, this is the work with my students Seung-Min An and Ki-Wan Jeon. Okay, this is contents for my talk. Let me introduce the first the MREIT. So what is the MREIT and the main algorithm which is used in MREIT, which is called harmonic BG algorithms. And I will review some of the PDE-based denoising method, and finally I will introduce some modified lamp-preserving Han and Lee method. And I'm not familiar with that name, but this is my name. This is my student Han Ju-Young's name. But okay. And finally, I will give some numerical experiments and the conclusions. Okay. So so what does the MREIT stand for? Okay, so MREIT means magnetic resonance electrical impedance tomography, and it shows some conductivity image using the MR machine with current injection. So look at these pictures. Okay, so this is MR machines, and the human being is inside this MR machine, and here's the electrode. So we inject the current through this electrode, and then this this current density induces magnetic flux density, and then this MR machine measures this z direction component of magnetic flux density, and it gives some images. So we call this is conductivity images. Okay. So this is the mathematics related to this MREIT. So we denote sigma as conductivity and use electric potentials. Then inside this body, okay. So we assume this is body. Okay. So inside this body we have the elliptic equation holds. So on this electrode, so we inject two currents. So first we put the we apply the current from this to that, and another set is from here to that. So we have this I is the amount of current, and on this electrode we have the tangential changing of that potential is 0, and in other reasons, other boundaries, the normal changes is 0. Okay, so we have J is current density, and J is expressed minus sigma grad U, and we call this B is magnetic flux density. Then from the Ampere's law we have this. So this mu 0 is the magnetic permeability. So mu 0 Z is equal to the curl of magnetic flux density. Okay, so using this Ampere's law and Maxwell's equations, we have these relations between conductivity and electric potential and the magnetic flux density. Note that here we have a second derivative. Okay, this is Laplacian. Okay, so from these relations, we just look at the only z direction component. Then we have these simple equations. Okay, so this is, so you put the sigma here and divided by sigma, then you have this point. So this is actually the curve of the current density Z. Okay, so we have two currents. We have two electric potentials. So you obtain these equations. So solving these equations, you obtain the sigma. Okay, so we solve this there. Okay, so from these observations we have the harmonic BG algorithms. So first we assume there's some initial conductivity. Okay, and using that initial conductivity we solve these elliptic equations inside with their boundary conditions. Then we have some approximated potentials, and using that potentials. Okay, so we have two set currents, so we have two electric potentials. Okay, so using that, we find these equations and find the sigma. Okay, then we go to here. Okay, again from that updated sigma, okay, we find this electric potential and use that again update the sigma. This is basic the harmonic BG algorithms. Okay. So if you look at that, okay, this BZ comes from the MR machine. So, and also it has the Laplacian BG. So that means we take second derivatives. That means if BZ has some machine noise, then we have lots of trouble here. Okay, so we need to denoise, okay, to this BG data. Okay, so in order to introduce the denoising method, okay, we just briefly review what is very standard in the denoising world. So the simplest one is just this isotropic smoothing. So if you look at that, okay, so this is just heat equations, okay, and okay, so. And the second thing is Perron-Marling model. Perron-Marling model is, okay, here you have a different coefficient. Okay, so this is diffusion coefficient in heat equations. So this is, okay, assume that 1 of square root of that. So it depends on the magnitude of changes of the image I. Okay, so this is image and near edges. Okay, near edges we have a large gradient I, and then this means this is large, that means this G becomes small. So that means near edges it has the small diffusions, and near plane regions it has it gives larger diffusions. Okay, but in actually if you compute that, then it shows some anisotropic diffusions. So along that edges it diffuses, but across the edges it gives small diffusions. Okay, so that is basic the idea of Perron-Marling method. And actually, the Weikert developed that algorithm, that method. So he used here some tensors instead of the scalar coefficient. So he used tensor informations, and so my student Zhu Yonghan and I modified that Weikert method, and we developed a method which will be appeared in Journal of Mathematical Imaging and Vision. And here, if you look at that, okay, so here the image is here. Then, yeah, so the first you take a gradient of I, and we make tensors, okay, and we regularize the tensors. And actually, the Weikert uses the first derivative information. So that is very standard denoising. But here, we use these tensors to denoise this image. So we think about just the informations of image, not the informations of the tensors. So instead of using the first derivative of tensors, we just use the first derivative of image. That is just U. Okay, so it gives different PDE. Okay, so using that regularizations, okay, we have smooth tensors, and we use that here. Okay, so we denoise this image using these tensor regularizations. Okay, so this is image denoising part and this tensor regularization part, and this GU is expressed as that. So we have this is the maximum eigenvalue, this is minimum eigenvalue, this is the corresponding eigenvectors. So this is in a sense, the same as the Perron-Marling model, but we have more freedoms to choose these tensors here. Okay, so in Han Li method, we have some eigenvalue analysis. So we have the maximum eigenvalue, minimum eigenvalues. So if you compare the minimum eigenvalue and the maximum eigenvalues, then we can find which where we have some edges, where we have noise. So if lambda is small lambda is large, that means this maximum eigenvalue, minimum eigenvalue, both large means we have the noise or we have corners. But in this BZ image, we have no corners, so that shows that is noise. Okay, so that is just the mathematical descriptions. And our target is, okay, this is BZ images. BZ image, the noise, the BZ images. Okay, and from this, if we construct this conductivity images, we have this kind of noisy images. But if we denoise like that, actually this is original image, but if we are successful to denoise like that, then we have this very clean image. Okay, but actually we made this noisy image from that. Okay, so so in our cases, if you recall that we have a second derivative of a BG image. So we need to preserve the ramp structures of that images. Okay, ramp structure means we need to keep the critical point of that images. Usually the denoising method preserves the edges, but here we don't care about the edges. We only care about the critical point of that images. So we change the structure tensors. So instead of that a derivative or first derivative of I, in a sense we take a second derivative of I, okay? Second derivative of images, and we choose that as the initial structure tensors, and we follow the same Hanli method. Okay, yeah. So if you look at this is original image. This is the synthetic image. So this has the lamp structures, the large of lamp structures. So this we put some noise. This is isotropic smoothing. This is Perron-Marling method, and this is ramp preserving Hanli method. So if you look at that this seems best. Okay. But if you use in these schemes in BG denoising, we have a lot of trouble because actually in a BG image, the magnitude of the image is very small. That's a 10 to the negative 7. So if you use this idea, then the magnitude is very small, and the maximum minimum eigenvalues are also very small. So it gives the almost isotropic smoothing. So in order to overcome that situations, first we changed the data range to the normal image. Normal image means the image ranges from 0 to 255. And also we put some scale factors depending on the noise types. Okay. So we just test several things. And the first case is we put some randomly distributed noise for this case. Okay. And then just we take the constant H, the scale factors, okay, and for the second case, for the salt pepper type noise, okay. So if you look at here, okay, so this comes from some real BG data. So in this case, if the small eigenvalue is bigger than some threshold, we call that we say that is noise. So in that case, we have isotropic diffusions, and if that is less than so the minimum eigenvalue is less than some numbers, that means the noise is along some the critical point. Okay, so in that case we need to keep the structures of the images. Okay, and also so in order to find that threshold, we first take some averages and standard deviations of the small eigenvalues of each pixels. And also, as time evolves, the noise will be reduced. So we increase this factor. So okay. So first, from these clean images, we put some noise. Okay. So we put some noise from the Ampere's law. Okay. So so we add Gaussian random noise, and from this we obtain this noisy BG images, not BG images, noisy conductivity images. Okay. So in this case, now we have the scale factor as a 10, and we measure the SNR and the relative H1 norms. So here, if you look at that, okay, this is okay. So from the isotropic smoothing, from the Perron-Marling method, and this is our method. Okay, so this is seems a little bit better. But if you look at the mathematical norms, so if you look at SNR, then our method is best. And also, if you look at the H1 norms, then also this seems best. And this is real BG data. Now, from the AGA phantoms, okay, we obtained the BG data from the MRI machines, and it really contains noise. Okay, and we use the scale factors H lambda equal to 100, and from that we obtain this. Okay, So yeah, so we didn't use that denoising algorithm yet. Okay, so without the denoising, we have this conductivity images. Okay, and you have some noises around that. Okay, so if you look at here, okay, so this is without the denoising. Okay, this is image without denoising, and this shows the several cases, and yeah, this isotropic smoothing, paranormalic, and modified paranormal. Modified paranormalic is actually designed by some other people, which will for the purpose of using the in the MREIT case. But here, if you look at our method, okay, this seems most similar to this image. Okay, yeah. So we have this sharp, slopes, and now we applied our algorithm to post-mortem canyon brain. Okay, so canyon brain means the door. Okay, so this is real busy data, and we have this proposed scale, and we have this threshold is changing. Okay, so yeah, this is dog, and yeah, we just look at this part. This is white matters and the gray matters. Okay. So this is the image without the denoising, conductivity image. Here is a lot of noise, and so we use several denoising methods. And if you look at that here, we have the significant this shape, these M-type shapes, okay, and we have no noise here. But in this case, okay, noise is still living, but this M shape is not significant. Okay, so. Yeah, this conclusion of my talk. Okay, so we modified the honey method, and we modified the lamp preserving honey method, and okay, so we changed the data range to the normal image, and we get some scale factors. Okay, and also we use that for the simulated phantom, expanded phantom, and the post-mortem canyon brain. So the main success is based on the magnification of strength of lamp, and we can identify salt pepper time noise by eigenvalue analysis. And for the salt pepper time noise, okay, we use isotropic smoothings. Okay, thank you very much.